Hey everybody, this is Rhett. Welcome to Statistics. In this video, we'll be looking at the basic process of hypothesis testing. Let's look at an example. According to so-and-so, the average time spent weekly studying for a 3-credit-hour college class is 6 hours. Harry thinks the average is different for an introductory stats class. Let's state the opposing hypotheses. We'll test Harry's theory. In other words, we will test whether the mean time spent studying for a statistics class differs from the mean of 6 hours weekly, which is for all 3-credit-hour college classes. The alternative hypothesis is that the mean does not equal 6. The null hypothesis states that the mean for stats classes is the same as the overall mean. Before we begin the test, let's agree to a few assumptions. First, let's assume that the population distribution of study times is normal. Secondly, let's assume that the population standard deviation is known. In this case, let's say that sigma is 2 hours. In any hypothesis test, the null hypothesis is assumed to be true. The null hypothesis, H0, is mu equals 6. We will gather data, in other words evidence, from a sample of size n equals 16 randomly selected students in an introductory statistics class. This is a test about mu, the population mean. So we'll use x bar, the sample mean. So let's consider the sampling distribution of the sample mean, x bar. Is the population distribution normal, or at least approximately normal? Well, one of our assumptions was that the population distribution is normal. If that were not the case, we would look at the sample size. Is the sample size at least 30? If so, we can apply the central limit theorem. We need to verify that at least one of these conditions is met before we proceed. Since the population distribution is normal, the sampling distribution of x bar will be normal. The sampling distribution has the same mean as the population distribution. The standard error is sigma over square root of n. According to the null hypothesis, the mean is 6. By assumption, sigma is 2. Our sample size is 16. So, the sampling distribution of x bar is normal, centered at 6, with standard error 2 over the square root of 16. Which simplifies to 1/2. Here we have a normal curve labeled according to the assumed distribution of x bar. Assuming H0 is true, 68% of sample means will be between 5.5 and 6.5. 95% of sample means will be between 5 and 7. And 99.7% of sample means will be between 4.5 and 7.5. This is all based on the assumption that mu equals 6. Now that that's settled, let's consider a couple of scenarios. In the first scenario, our sample mean is 6.2. Does this evidence contradict the assumption that mu equals 6? In other words, is it so extreme, unlikely, or rare that we dispute the null hypothesis? This evidence does not contradict the assumption that mu equals 6. If the population mean is truly 6, then a sample mean of 6.2 is not unusual, and so we fail to reject H0. Let's consider a second scenario in which x bar is 4.2. Does this evidence contradict the assumption that mu equals 6? Is it so unlikely or extreme that we dispute the null hypothesis? This evidence does contradict the assumption that mu equals 6. If the population mean is truly 6, then a sample mean of 4.2 would be an extreme, highly unusual, or very rare result. So much so that we reject H0. In a third scenario, x bar is 6.9. Does this evidence contradict the assumption that mu is 6? Is it so unlikely or extreme that we dispute the null hypothesis? In scenario 3, the evidence is not clear. We need a definition of extreme in order to make a decision regarding H0. How do we define extreme? We need to draw a line in the sand. If the test value crosses that line, then we consider it extreme, in which case there is sufficient evidence against the null hypothesis, and we reject H0. If the test statistic does not cross the line, then we do not consider it extreme. Thus, there is insufficient evidence against the null hypothesis, and we fail to reject H0. There are two commonly used methods for drawing this line in the sand. Both are based on alpha, a level of significance. These methods are the critical value method and the p-value method. We'll look at each of these in separate videos. In this video, we looked at hypothesis testing in practice. We assume that the null hypothesis is true. We gather evidence from a sample. If the test statistic is extreme, then we reject the null hypothesis. There are two commonly used methods for defining extreme, the critical value method and the p-value method. Thank you for watching and have a great day. Until next time, stay real and be rational.